In the next few classes, we will shift our focus from how we detect differences between groups by analyzing mean scores to how we evaluate hypotheses concerning correlations between variables. In psychology, we are frequently interested in the relationship or correlation between variables. We might ask whether depression is correlated with absenteeism from work. Similarly, we might ask if locus of control is related or correlated to someone's ability to recover from trauma. Finally, we might ask if overall life satisfaction is correlated with ratings of one's own physical health. A research hypothesis would result if we hypothesize that scores on a measure of life satisfaction, for example, would be positively correlated with scores on a measure of the adequacy of one's personal health, with high scores on both measures indicating satisfaction. Note that the correlation coefficient in the population here in your slide is expressed with rho, or the Greek symbol for R. Please be aware that this is not a P or probability. The null hypothesis is that the variables are not correlated in the population, or that the variables are independent in the population. The t-test is used to test hypotheses concerning the Pearson correlation coefficient. Remember that the Pearson correlation coefficient is used when variables are measured using interval or ratio scales of measure. The basic form of the t-test for the correlation coefficient is evident in the formula. The statistic of interest, the correlation coefficient, is in the numerator, and the standard error of the correlation coefficient is in the denominator. Because we compute a mean for each set of scores, degrees of freedom will be equal to n minus 2, where n is the number of participants or the number of pairs of scores. Before going to the next slide, imagine we had a sample of 62 participants and administered a measure of life satisfaction and a measure of one's rating of their own health status. Let's assume we obtained a correlation coefficient equal to 0.36 and that the standard error for the correlation coefficient was found to be 0.11. What is the t-statistic for these data, and would we accept or reject the null hypothesis? We would compute t by dividing the correlation coefficient 0.36 by its standard error 0.11, and the result would be the test statistic of 3.27. From the t-table, the critical value is 2.00 when we use a two-tailed test with alpha equal to 0.05 and degrees of freedom are equal to 60. Which is computed by taking n, 62 minus 2, and so degrees of freedom are 60. In this case, the test statistic exceeds the critical value, and we would reject the null hypothesis. We would conclude that the variables are positively correlated. We can also construct a confidence interval for the correlation coefficient using the same general formula we learned for means tests. We merely take the statistic of interest, the correlation coefficient, plus or minus the product of the standard error associated with the correlation coefficient and the critical t-value used to test the hypothesis. In addition, the rule of thumb concerning the confidence interval and hypothesis testing will also apply when we're working with a correlation coefficient. Thus, a confidence interval in which the value associated with the null is not included in the interval will lead us to reject the null. And remember that 0 is the value most often associated with the null when we are testing the correlation coefficient. Thus, if 0 is included in the interval, we would retain the null. Before going to the next slide, see if you can construct a 95% confidence interval for the finding we discussed in the last slide. Also, then determine if you would accept or reject the null based upon the results of the confidence interval. The answer is that the 95% confidence interval will be 0.14 to 0.58. We compute the confidence interval by taking the correlation coefficient 0.36 plus or minus the standard error for the correlation coefficient 0.11 times the critical value for t at the appropriate degrees of freedom, which is 2. Thus we have 0.36 plus or minus 0.22 and wind up with our confidence interval. We would interpret this interval by saying that we were 95% confident that this is an interval likely to contain the correlation coefficient in the population. In addition, we would reject the null hypothesis because the value associated with the null, which is 0, does not fall within the confidence interval.